Welcome back to the Pathfinder's Codex. This is the third video in the beginner series, and we're going to introduce some new concepts and reinforce some ideas from previous episodes. We have 4 new practice shaders to cover today, and we're going to pick apart each one to see how they work. We'll start by revisiting the concept of color mixing, and manually converting a hue to RGB to make a rainbow that repeats and shifts over time. We'll learn a new way to blend the original texture with the new effects using interpolation. Then, in the second shader, we'll combine a bunch of techniques we learned so far to create some rotating and fading effects. We'll use it to create some procedural glass marbles. In the third shader, we'll introduce polar sampling for edge detection and drawing outlines, a lot of uses for highlighting characters, icons, or interactive elements in your games. And finally, in the last shader, we'll generate a flickering border using procedural noise, giving your sprites that extra magical, glitchy, or fiery appearance. Alright, let's get to it. First up is a warm-up shader, the ShiftingHueGradient shader. This shader lets you control the strength, speed, and angle of the color shifting effect. Let's build it from the ground up. First, let's split the texture into 2 parts, left and right, and set it up so we can rotate it around the center of the texture. We're converting our input angle to radians here because Godot is sending in degrees between 0 and 360. That'll give us the rotation effect. And we're centering the UV by subtracting vector 2, 0.5 like we did in many of the other shaders we've seen so far. Then, we'll decide the output color. It'll be grayscale for now, and it'll wrap between 0 and 1 starting at the center of the image. We'll use the fract function to ensure we have a loop. This function returns the decimal part of a floating point number, which is how we'll create the looping values that are always between 0 and 1. We can test the rotation logic by changing the angle uniform to make sure it's working. Okay, now that we have the rotation and looping color, let's add the animation by using the time variable we learned about in the last video. And we'll make it configurable using an input speed uniform. We can change the speed of the color movement using this input. Nice, now we have both the animation and the rotation logic in place. Let's add the colors. Right now we have the color set to a single looping color band, from black to white, from 0 to 1. First, we'll break that value into 6 RGB color segments. The colors are broken down into 6 segments, where each segment represents a gradient from one color to the next. Why are we doing it this way instead of using the awesome HSV to RGB function that we learned about in episode 1? Well, it's easier for artists and developers to understand and tweak specific color ranges when using the if statements, instead of a hard-coded formula. The end result is the same. We converted some hue bands to RGB, but now we can make further adjustments to any of the segments depending on the art style of the game or the needs of the graphics artist. Now, to finish up the shader, we'll finalize the image by mixing in the new color with the original texture's color. And we'll control exactly how much blending using a strength input variable. A strength of 1 fully overwrites the original image, while a 0 completely hides the new color effect. And there we go. We have some basic input controls, and we can use the shader for some simple effects in our games with just these options. And we could even expand the code that creates the 6 bands for even more control if we don't want the generic rainbow pattern. Great. Let's move on to the next shader where we can create some neat rotating marbles. The WaveRotateBlur shader. This one's hard to describe. We're not really introducing new concepts here, we're just combining ideas we already talked about in different ways. And in this shader, we're completely overwriting the original texture, so it doesn't really matter what sprite we put it on because we won't see that sprite. The end result is a customizable image that resembles a fuzzy glass marble, where we can control different parts of the patterns on the rotating disc. Probably easier just to show you the nuts and bolts. First, we're going to make a temporary circle. We'll set up a distance-based fade-out and allow the developer to change the size of that circle using the scale uniform. This gives us the fuzzy circle mask that we can make bigger or smaller using UV scaling. We'll apply that scaling zoom using square root to make the adjustments more gradual. And of course, it's centered in the UV space like many of the other shaders we've worked on. Okay, to make the rest of the shader easier to understand, I'm going to turn off this scaling and the fuzzy ball, and we'll come back to them in a second. Next, let's create a sine wave pattern and animate it. Nothing new here, and we've seen these concepts in previous shaders even if not in this exact setup. Here, we're rotating the entire wave pattern around the center point, and we can change the speed of the rotation using the speed input uniform. Okay, now we'll add 2 source color pickers, and have the sine waves use those colors instead of always using black and white. We can pick whatever colors we want, and they'll blend seamlessly from one hue to the other. I've also added some new input uniforms, so we can control different parts of the wave and rotate animation. We'll touch on those in a second. Perfect. With the color blending and the rotation working, we can bring back that fuzzy circle. We'll blend it in as transparency on top of our rotating waves. The end result is a spiraling circle that has the appearance of having an atmosphere. We also added more input uniforms. Each of these control different aspects of the rotation and motion of the effect. With those input settings in place, we can make the sine wave move, not just rotate. We can control the offsets of the animation and the rotation. We can decide how many waves it has with the frequency setting. And we can adjust the intensity of the blurring effect using a contrast input. I played with this shader a bunch and found that it makes some interesting marbles or pips that might look good in game interfaces. It could definitely be useful for procedurally generated textures. Here are some of my favorites as I was playing with the different uniform settings. Let me know what else you think this Gabor-like pattern might be useful for. The next shader takes a concept we learned in the last video for making an animated border and applies it to the sprite's pixels instead of the bounding rectangle around the texture. Let's check out Animated Border version 2 and do some basic edge detection. This one's great for highlighting selected items, adding glowing borders to your sprites, or emphasizing interactions in UI elements like menu items. Let's walk through it. First, we'll capture the alpha transparency from the original image. This gives us the transparent parts appearing black and the opaque parts appearing white. It's a grayscale mask showing where the sprite's pixels are. Next, we'll increase the size of the shape by detecting the edges and padding it with extra pixels. We'll use the built-in texture pixel size variable, combine it with our line thickness uniform, and use that to grow the shape in each of the cardinal directions by a certain number of pixels. That special texture pixel size variable gives us the exact size of one pixel in UV space. So when we combine it with line thickness, we'll be working with a true pixel size, which is useful especially when we're working with pixel-perfect effects. Here's how the outline logic works. Picture every pixel in your sprite as a little square on a grid. For the pixel the shader is currently drawing, we peek at its 4 closest neighbors, one step left, right, up, and down. We do that by nudging the UV coordinates in all 4 directions, where size is exactly 1 real pixel thanks to texture pixel size. The code determines how solid each of the neighbors are, where 1 is completely opaque and 0 is completely transparent. When we add up all of those alpha channels, we'll get an outline total. What does this running total mean? If all 4 neighbors are transparent, then the total will be 0, and we know this pixel is out in empty space. If at least one neighbor is opaque, even a little, then the sum will be more than 0, and we know we're touching one of the sprite's pixels or edges. To make things more crisp, we use the step function like a light switch. This way, we won't have to worry about partially transparent pixels, and we can just assume that any given pixel is either fully on or fully off. And if we wanted to, instead of using the step function, we could also do this with a rounding function. Our outline shape is now a clean black or white mask. In short, the shader sniffed the pixel's immediate neighbors. If any of them were solid, we marked the current pixel as part of the outline. So now we have a mask that includes a thin outline around our shape, and we can control the line thickness. We only used 4 cardinal directions when we sampled the texture UVs, which works in most cases, but let's make it more robust by including additional samples. The transparency check logic will be the same as before, but now we're sampling 12 points instead of 4. We'll include the diagonal pixels and even check some half pixels for finer control. This creates a fuller, rounder, and smoother outline. Now let's break down the texture into 3 distinct areas. To do that, we need to check a few things. First, we'll check the original texture's transparency. If we're less than half transparent, we'll assume the pixel is from the original image. If we're not inside the original sprite, maybe we're on the border. To check that, we can use the outline total we just created. If the outline value calculated is more than 0.5, we'll assume this pixel is part of the border shape, and we'll color that red. And finally, if the pixel is neither part of the original texture and it's not part of the shape area, we'll assume it's a transparent pixel. For now, I've made this last area white so we can see the 3 distinct areas. But when we finally change that to be transparent, we'll see the border that we want around our image and all the transparency is accounted for. Making progress step by step. Okay, now let's add the animation effect. To do that, we'll use the same technique we used in prior shaders to create a rotating set of arms in a circular pattern. To make it easier to visualize, let's hide the original texture pixels for a moment. Okay, now we can add the time-based animation. First, we'll add a few input parameters to control the color, the frequency, and the speed of the animation. Then in the fragment function, we'll use the arctan function to get our pixel's angle from the center to create the arms, and use the time and speed variables to make them rotate like we did in previous shaders. This adds a radar-like rotation to the area covered by the outline variable. It changed from red to white because now we're using the line color input setting, but otherwise this is our rotating circle infused onto our border shape. Neat. And now we just need to re-enable the original sprite's pixels to see the finished results. Looks good. We can choose our border color, speed up or slow down the rotation, change the line thickness, and control how many dashes we want using all of these different input parameters. There are a ton of ways to detect borders, some better than others depending on your needs. But this is one of the easier ways, especially if you don't need complex logic. Let's make another border effect, this time using noise to generate a flickery, almost fire-like effect around our texture. The last shader for today is FlickerBorder. This shader is perfect for some pretty common effects like energy fields, magic sigils, or fiery sprites. It uses polar sampling for edge detection to create a flickering border around the pixels of the texture. We'll use some procedurally generated noise to create randomized but smooth variations in the effect. We'll start with the polar sampling and the edge detection, and gradually layer on time-based flicker and procedural noise, until we land on the final dynamic outline that you see here. Here's the gist. First, we need to know where the texture's pixels are. We'll sample the alpha channel at the current pixel UV. Anything below about 0.1 we'll treat as empty space, and we'll tint it bright red. Everything else will pass straight through. This quick pass gives us a mask of the silhouette and confirms our threshold is catching the transparent pixels. Next, we detect edges by sampling around each pixel in a tiny circle. This polar sampling will check if the current pixel is next to any non-transparent pixels. We'll need to add some constants for the shader. This angle res constant is how many samples we'll take as we move around the circle. So there will be 16 rays over the 360 degrees. In the fragment function, we're going to use the special texture pixel size variable again, like in the last shader. This way we can always be sure that we're jumping outward full pixels in every direction. Now we'll loop over the circle, once for each ray. Each ray adds the alpha it finds. If the sum is greater than 0, but our current pixel is still transparent, we know we're on a perimeter. And we're making it bright green to prove it's working. Looks like a border to me. A static outline is fine, but a flicker will bring it to life. First, let's add a frequency uniform so we can control the input. Good. And here, the time variable counts up each frame, multiplied by the frequency input, and flooring it to get discrete beats or pulses. We modulate the circle's radius with a small sine wave every beat to make it oscillate back and forth. The result is the tremble you see here in the now yellow border that pulses over time, perfect for things like sci-fi energy shields or item selection highlights. But let's take it a step further and rough up that border by making it noisy. We'll do that with some new input uniforms and a tiny pair of helper functions, hash and noise. The hash function will give us a repeatable pseudo-random value for any 2D point on the grid and any seed we give it. The noise function then uses 4 of those hash values and mixes them together. So instead of hard jumps, we'll get smooth hills and valleys, which gives us a more natural noise feel. And to use those two helper routines, we'll add one more function. The getLineWidth function blends together 3 layers of noise, called octaves, each adding finer detail at lower intensity. It scales the sampling location using a customizable block size. In this case, that means that every 3/4 pixel square shares a value, giving us chunky but interconnected details between the actual pixels. The value is then mapped between our desired minimum and maximum line widths, to give the border its organic uneven motion. This can result in positive or negative widths, where positive line widths will push our sampling circle outward, while negative widths will pull it inward. To bring it all together, we'll use these new functions in our fragment logic. And we'll add a color picker for the developer to choose the border color. The shader does 4 quick moves during each frame. First, the beat sync. It grabs the time step, which is our integer frame counter ticking at our desired beats per second. Second, the noise scale. It uses texture pixel size and getLineWidth, so every pixel decides exactly how far its 16 radial samples should reach out. We feed the current pixel's UV position into that line width function as the first parameter. And for the seed, we pass in that time step. So the noise changes once per flicker beat, not every frame. That keeps the noise motion smooth and stable without any harsh or jarring changes from frame to frame. Third, the polar scan. It marches around the circle for each ray, looking for opaque neighbors at the scaled offsets. And fourth, the painting. If we're sitting in an empty space but any neighbor is solid, we'll use the outline color uniform. Otherwise, we render the original sprite pixel untouched. The result is a border that flickers, crawls, and never quite repeats, ideal for magic sigils, crackling force fields, and your fiery sprites that need a bit of chaotic life. The outline now breathes, swelling, shrinking, and wriggling like living energy, and we can adjust the effect with any of the various input uniforms. Looks great, and it's a powerful introduction to using noise in a shader. This type of noise is known as value noise. There are lots of kinds of noise, and they have lots of different uses in game development. In future videos, I might spend some time going over noise in more detail and some of the cool things that you can do with it. And that's the FlickerBorder shader. Today we looked at some practice shaders that were a bit more complex than those found in the first 2 videos. But really it boils down to just 3 new concepts: color banding and mixing, pixel sampling and polar sampling for edge detection, and using procedural noise to add randomness to the effects. These techniques unlock a ton of creative options, so feel free to play with them and start adding them to your shaders. Stay tuned for the final video where we'll wrap up the series with the last 4 practice shaders. If you're enjoying our videos so far and you want to help support the channel, be sure to subscribe. And it's extra helpful if you can leave a comment, a question, or even suggestions for future videos that you might want to see. Don't forget to check out all of these shaders and support your awesome shader developers over at GodotShaders.com. Thanks for watching the Pathfinder's Codex, and as always, never stop learning.